Okay, I think we are now on our discussion on symmetrical fault calculations. So we're doing EE triple E222 or fault tolerant power systems. So we will now discuss part 4, the symmetrical fault calculations. And again, this is covered from module number 1, as a problem set, for the module assessment. Okay, so we'll not go to details anymore of some of the lectures, since we already described that one, and you already have a recap of what we have discussed in the last few meetings or modules on on the basic fundamentals. So last meeting we discussed symmetrical components and the application to power systems and problems on faults and unbalanced polyphase. Now it will now be applied here on some of the calculations, especially the first type of fault, which is symmetrical fault calculation. Okay, let's move forward. Okay, now alam naman natin a fault is any interference with the normal flow of current. So may tinatawag tayo two things here. May tinatawag ka na overload at may tinatawag ka na overcurrent. So kapag overload, this just 10 times, Ang overcurrent is 20 to 100 times of the normal current. So yung tinatawag natin full load current. So kapag sinabing overload, it's just a little bit of percentage lang ng overcurrent. Kasi yung overcurrent can be 20 to 100%, while the overload is just simply at 10% alone. And very clear, if there's a fault, it is a very, very big, in terms of value, in terms of the magnitude. So fault is nanggaling yan, it is originated from a flashover. So a flashover is if there's a two wires from a three-phase, 3-wire, for example, you have a three-phase 4-wire, and then one of the conductors here is ionized. When you say ionized, meron ng skin effect. So for example, the conductor is exposed, and then from there, okay, from skin effect phenomena, okay, from the skin effect phenomena, there the conductors will the potential difference between the two conductors are very are large, so that it can produce an ionization path between two conductors. And if there's an ionization path, then definitely it can yield to a short circuit, and from here it is a short circuit in a line-to-line basis. Now that is for if you have two wires, or tinatawag nating two-phase fault. Pero if the wires are short-circuited simultaneously, A, B, and C, in this case, then you have a symmetrical fault calculation. Now, since the three wires are being short-circuited, it will produce balance fault currents, and those balanced fault currents is so-called a symmetrical fault current. Kaya if you see this variables here, IFA, IFB, IFC, it means fault current at phase A, B, and C, and there are balance. And if this is balance, okay, fault A, fault B, and fault C, the only difference is they are 120-degree apart. Okay, so that's why it's very important that you already know how to per phase analysis, so balance polyphase. So that's why in our first few video modules, we concentrate on basic fundamentals. Okay, let's clear this up. Tapos move forward na tayo. Now, ito yung sinasabi natin. Okay, the short circuit must be after the load. It must not be on the load itself. The load that I'm talking about here is this load. Okay, the load is balanced simply because, as you can see, the per phase value of that load is R, which means a variable which has equal value. Okay, that is for an example alone with an AC source, so resistive load siya. And then from here, the short circuit occurs here, and it will develop three vectors, which is IFA, IFB, and IFC, respectively. Now, the source that I'm talking about here, this is the balance source, from A, B, and C, and you have here, your per phase sources, It is not presented here, but ganyan niya. Ay, so sorry. It must have a source here, like this, and then from there. Ayan. So, meron kang VAN dapat dyan, VBN, and VCN. And from here, now, if you want to get the full current, it's very obvious that you need to use PPA. So, you can have a per phase basis here at A. And at the end of the day, it will become like this, right? If you have a transmission line, and then you have your resistive load, your R, your transmission lines ATL. Now, the fault occurs here, all right? No? Doon sa load natin, which it is clear though that you can get the short circuit current at F, which is the fault at A. Okay, now they are the same thing in terms of phase B and phase C, but we always use per phase analysis at phase A in order to get that fault current. So ang tawag dyan is the positive sequence, no, network. May negative pa, and there is a zero network, and then from there, if you develop all of those networks, it will, we can compute, no, for the different kinds of fault. But as of the moment, no, we concentrate on this ISC three-phase, which is your, no, symmetrical fault curves. Kaya ang topic is symmetrical fault calculations. And if you have a power system, no, it's very important that you know the modeling techniques. And then from there, no, from the modeling techniques, no, you can have the positive sequence network. From the positive sequence network or the PUEC, what you will do is to get the short circuit current definitely. And then from there, you will use a little bit, no, of your circuit analysis using Thevenin's theorem. Okay. Now, for this, we can clear this up, no, so that we can move forward. Now, the short circuit can be limited though by the impedances of the system up to the fault point, which means, no, if you have here your diagram, single line diagram, you can use, no, the per unit equivalent circuit, what we have discussed to you in terms of asynchronous lecture, and then we can have, no, this scenario, diba? If your generator has a XG here, your transformer as an XT, your transmission line has a ZL, and you have your load, for example, a Z load for this case. And the fault occurs, no, before the load, as mentioned here. Now, you cannot get the full current here, no, by having, this is we call, no, the voltage per unit. Okay? Ang tawag din dyan sa VPU na yan, no? I forgot to mention. This is VGU, this case. Voltage per, for example, you have 1 bar 0, no? In this case, in this manner, no? And then it depends on the modeling, ha? It depends on the value of the actual, it must be here. It depends on the value of the actual voltage divided by the base voltage so that you can get that VG per unit. Because if you regionalize systems, it is like this, right? Region 1, region 2, and region 3. Okay, now, the importance of having, no, the modeling parameters here, you need to know these reactances. And that's why it's very clear that you need to have the percentage reactances. So please take note. For example, this is also JG per unit. The only difference between the two is you multiply or divide by 100. It will become a decimal or, no, percentage. Okay, in this case, if you want to get the full current at that point position, I could say ISC at F, no? So what will happen is you need to use, no, the Thevenin's theorem in order to, no, get the short circuit. And how you will do that, the only way to do that is you need to know what is the Thevenin's reactance at the fault point and what is VPU or the so-called VTH at the fault point. Okay, this is what I meant a while ago, yung VPU. The VPU here is the so-called pre-fault voltage. Okay, without further ado, in order to get that pre-fault voltage, okay, in order to get that, is you need to have this formula. The formula is V actual, okay, on the generator, no? This is before the fault. And you divide it by whatever the base voltage is. Please take note, kaya nga sinabi siyang pre-fault voltage is before the fault. And the difference between a post-fault is that is post-fault analysis na you want to get, see the stability studies, reliability studies, frequency stability, voltage stability. Now, those are different things. You're considering transient behavior. But here, before the fault, kailangan makuha mo yan, yung pre-fault voltage. And in order to do that, we have this formula here. And please take note, in order to get the Thevenin's reactance, di ba, you need to, all of the sources must be equal to 0, right? And then get the reactance or impedance up to the fault point, no? Kaya nga XTH up fault F. Now, the sources that I'm talking about here, it can be a current source or voltage source. Now, definitely, will not make use of the current source. At lahat naman is independent sources, di ba? Generator na, that is already independent source. So, it means that if you want to get the source at equal to 0, you need to shorten, okay, that source. And in order to do that, again, if you want to get the Thevenin's reactance, may tinatawag tayong reactance diagram. In order to do that, you need to short all of the sources and present that shorted source by its corresponding reactance, which is I have mentioned here. This is your XG. Ito po yung PUEC, ha? What we have done from our separate lecture on synchronous lecture. So what will happen? Ganito nalalabas dyan. Ang tawag dito is your reactance diagram. So this is your VS equal to 0. You have your XG. You have your XT. You have your ZL in per unit and your fault. But whatever happens, kahit may impedance pa yan, okay, the fault point occurs here. So you need to measure the impedance from XTH at fault F to the neutral. So this is not this is the same, if you can still recall, your circuit analysis, sasabihin ng prof, what is the Thevenin's reactance up to points A and B, di ba? That is also the same thing. By opening the circuit, di ba? By opening the circuit, parang open circuit voltage siya, then all of the complex circuit will be represented by a Thevenin's reactance and the PTH, right? And then you can get Norton's current, which is the short circuit. And that's why, your XTH is definitely, if you add, all of the reactants here connected in series, right? XT plus XL plus ZL. This is only the Thevenin's reactance. Hindi kasama yung Z load. Why? Because open siya. And if you already have your XTH and consider your VPU, okay, depende yan sa formula, ha? Actual over the base. If your VPU is equal to 1, and this is supposed to be, then this is your XTH at your fault point. And then this is A and B here. If you want to get the short circuit current, di ba? Ito yung sinasabi nga natin. If you want to get the short circuit current, you need to short terminals A and B here, which is, at the end of the day, this is your Norton's, this is your short circuit at F, which is equal to whatever your BTH divide by the Thevenin's reactance to fault. So a simple circuit analysis. So that's why it's very important that you know the percentage reactances of all of your elements. Simply because if you do not know this, you cannot solve the Thevenin's reactance, and in the end, you cannot solve the Norton's current. Okay, very, very, self-explanatory in this case. So we just refreshing your circuit analysis, because circuit analysis is very, very important as a basic fundamental in short circuit analysis. So you need, kaya nga siya analysis, you need a little bit of your circuits. And one important aspect there is the Thevenin's theorem. Meron pang tinatawag din tayo, no, one important din ay yung ano, no, yung tinatawag na superposition theorem. The superposition theorem is very important in getting the so-called, no, contribution of every rotating element. That is your generator and motor, which is also important, no, on relaying, protective relaying, no, yung sensitivity ng relay mo at saka sa coordination. Okay, now let's move forward. So this is just a limelight with you, no, ibig sabihin an idea on how you will compute for the short circuit. Now we can clear all the paths here. Move forward na ho tayo. And on a power system, sometimes, no, and typical, the resistance is neglected. Sa transmission lang naman talaga may resistance eh. And then, reactance is considered. Kaya nga percentage reactance. However, on our exercises, no, it can be, no, dependent, no, on the given. Arbitrary po lang yun for exercise purpose. Okay? So which means, no, what kung ano man yung ginawa natin, what we have done on the algorithm, sundan ninyo. Because that's the process, eh, right? So it is not a design, no, in our class. The important here is you know the method and how you will, no, solve, no, for the short circuit, for example, for the load flow, no, for the power flow, or even, no, the stability analysis. So you need to know, no, the so-called procedures. Okay, now let's move forward. Now we have some formulas here. No, we can use, no, the formula at equation 4.1 and 4.2 respectively. The only difference between the percentage reactance formulas here, if you use this formula here, the I full load, by the way, before anything else, is your base current. The base current, no, can be represented by this formula. Okay, this formula is being discussed na, di ba? From your per unit analysis. Now, the X here, by the way, is in per phase basis. At yung V dito ay naka-per phase din. Please take note, no, the voltage, no, at the fault point must be in a per phase basis. Ito yung V base at the fault point, ha? Okay, that's the base at the fault point. Now, if you use this formula, please take note it must be the total apparent power. Total apparent power. And the KB here is in terms of in a line-to-line basis. Okay, so that's the difference between the two. But again, the result is the same. Okay, so this is the formula or the modeling for the percentage reactance. If you already know, the reactance or the reactor in ohms. Please take note, the X here is reactance in ohms per phase. No? And then you can now, no, convert it to corresponding percent or per unit. Okay, clear all paths here. Move forward. Okay, now, how about, sir, no, how you will compute for the short circuit current? So as I mentioned a while ago, you can compute for the short circuit current by having a Thevenin's reactance. The pre-fault voltage divide, no, by the reactance at the Thevenin's at the fault point. Ito yan. At ito yung I Norton mo, which is your short circuit. But in this case, no, we can use, no, equation 4.2. No, 4.1 rather. And then you can, no, substitute here at this, you can substitute there, here at X, yung substitute equation 4.1. Now, it will yield, no, with this equation, ito yung equation, with this equation, yung 4.1, it will become like this. And then it will yield with this formula here. Now, please take note, no, the ISC here is an actual terms, no, which is equal to I base, I full load. And please take note, no, the 100 over percentage X here is based on IPU, right? If you can still recall, to get per unit is actual, you divide it by base. To get the actual, you need to multiply per unit by base. So in this case, ito dapat is I per unit, right? Because that is current. But IPU here has a formula, right? Has a formula kanina. This is your Norton currents, eh. Short circuit, VTH over XTH per unit, right? It must be the same thing in per unit. Okay. However, if you want to explore it in percent, you can do so, no, by multiplying 100 over 100. Kasi lalabas dito, other form ng ISC triphase eh. It can be, no, I base times IPU. But IPU is 1 all over Thevenin's reactance up to the fault point F. Or if you insert 100 over 100 in the equation, please take note, this is also I base. It can be like this in percent. So in other words, okay, to have a mnemonic, tandaan po natin, 100%. So ibig sabihin, taguro yan. Which means, kapag per percent, may taguro sa numerator. Kaya nga 100%. Okay? So yun lang ang technique. Kasi if this is 1 all over XTH, it means dapat ang XTH mo naka-per unit din. Pero kapag naka-percent ka, dapat may taguro sa numerator, 100. Kaya 100%. So that's the only difference between per unit and percent. But again, they will serve the same purpose. The formula of the short circuit can be equation 4.5 or this equation that we develop here, 1 all over the Thevenin's reactance. Please take note, by the way, this is not always 100%, huh? Because that will depend on the pre-fault voltage itself, okay, in per unit. Okay, let's move forward to the next few slides. Now, this is the change of base formula. And then you can get the X new here, or the X base, by having the X given or times S new over S given, or yung S base over S alt. Now, in this case, nawala yung yung V given over V base here. Hindi naman necessary na wala. It becomes 1. Simply because, if V given is equal to V new in the calculation, the answer is 1 per unit. Right? So again, this equation 4.6 can be used for a quick calculation. Considering again, the V given over V base is equal to 1. However, there are possibilities that the V given and V new are not the same, lalong-lalo na if you have a non-ideal or non-linear power system. Okay, now let's clear this paths here. Then move forward. Okay, now if you see here, you can get the short circuit current. You can also get the so-called KVA short circuit. In order to do that, nanggaling lang yan doon sa formula natin, VI, kaya KVA, there's no power factor. You multiply it by 3 so that it will become total. And if you divide it by 1,000, it will become a KVA. Now, if you can still recall, your short circuit, we have this form. Then, if we substitute ISC here at equation 4.7, yung 4.8, it will have equation 4.9, which is also the same thing if you use this times IPU. IPU here is 1 all over XTH at the fault point in terms of per unit. Please take note, this one here is equal to VPU over V base, which is your pre-fault voltage. So this is the same thing with this equation 4.9. We only extract the 100 over 100 there. Kaya tandaan po ninyo, 100% taguro, which means the percentage, if you have a percent reactance, dapat may sa numerator, may taguro, may 100. There must be a 100. Okay, we need to clear all paths. And then we can move forward. Okay. Now, this is just a little bit of information if you want to have reactor control. And if you have a reactor, it can be placed in series with genset, in series with the feeder, or even in series with the bus bar. Okay, and a reactor definitely is a coil which has a number of turns, which has a large inductance compared to its ohmic resistance in order to minimize short circuit. Paano po nangyari yun? It is based on a basic formula. which is a Lino-Luter formula. And definitely, the inductance is inversely proportional to the current. And if that will be the case, then, no, if you have a larger inductance, it can compensate larger current. So especially in terms of the magnitude, also on circuit breaker selection, right, on the design. So instead of upgrading that one in a new, replacing your circuit breaker with a new one, which is very, very expensive, you can place a reactor in series, no, which is sometimes practical on distribution systems para hindi po masyadong mataas o malaki yung maintenance o yung gagastusin. Or that's why, no, so it must be strategically, no, placed in a power system. Okay, now let us have the following. Well, I will not go to details of the advantages. You can read it out, no, on your own. No? Ang importante dyan, if you have a fault and if you have a reactor in series, it can concentrate or it can localize or it can separate that section to others. So para hindi na po pervasive o mag-spread yung fault from other section of your system. Okay, parang ma-isolate, in other words. Now you can have, no, the placement of your reactor. It can be a generator, it can be a feeder, and it can be, you know, on a bus bar. No? Okay, now in this case, no, we have this generator reactors, no, which is placed in series, no, with your generators. Definitely, no, this kind of setup is okay with all generators. But this is not practical, no, with the new generator, because we already know, no, this type of machines as already, no, is equipped, no, with the state-of-the-art protection. But again, no, if this is just, no, an alternative, no, for the design. Okay, so the number one objective here is to protect the genset. Okay, these are the disadvantage of that. And constantly there will be a voltage drop, no? Dahil may voltage drop ka dito bago ka pumunta until you reach, no, your feeder. Okay, ang feeder reactor naman, no, is located here at the feeder side, no? So which means this is practical simply because, no, majority of the faults, 80% of the time, no, comes from the feeder. If there's a fault occurs at feeder number 1, this is what I call, no, localized or isolation. If this is section 1 and section 2, before the fault reaches, no, the second section, okay, ano na siya? Extinguished na siya, right? Na-open na your circuit breaker or your fuse. It's already, no, in minimal state. Or in other words, extinguished na siya because of the reactor which is placed on your feeder. So before it escalates, no, his fault is already, no, in a minimum condition or minimum state. Okay, let's move forward. The advantages and disadvantages, I will not go to details anymore. But again, no, there are plenty of advantages, but there are also disadvantages because there is a continuous power loss and you need to upgrade, no, these reactors if you upgrade your generators. Now, the most practical one is your busbar reactor is placed in series on your busbar. So this is a typical example that the reactors are connected, no, between sections. So in this case, this is section number 1. This is section number 2. And this is section number 3. If the fault occurs at feeder number 1, before it escalates, no, on section 2 and section 3, it will be in a minimum state because there is a reactor in series with this, no, section. Okay. So that's why it's more practical that you can have the reactor in series with your busbar. Now, there's no power losses simply because, no, nakalagay nga siya sa busbar, right? And if a fault occurs on any feeder, naka-isolate siya, no? Or concentrated on that section only. Okay, we can clear this this path here, and then moving forward, we can move forward. Okay, now the most practical type of system in terms of the reactor types of reactor arrangement is a tie bar. The tie bar is twice the protection on a ring system. As you can see here, if you have your sections, we have section 1, section 2, and section 3 respectively. If a fault occurs at one of the transformers here, before again it goes to the another section, as you can see on this path, you have one reactor and you have another reactor here. So you have R1 and R2. The protection is twice, right? But again, it is expensive in terms of the on the setup because you need to install a tie bar. And again, this is inevitable already. Why? Because on this case, it's very clear that if you want to have a reliable protection, it is always a trade-off with cost, right? So, syempre, if you are the manager, you want to have a lower cost, but it greatly affects the reliability of the system. If you want to have a more sturdy design, then you need to have your cost. You need to invest on cost, right? But again, it depends on the situation, right? And on the condition of your power system. Okay, now, since we already discussed the basic fundamentals and already 4.10 and 4.11 is already discussed from the previous slides, this is the so-called 6-point algorithm. 6-point algorithm. 6-point algo. Because in this case, it has 6 procedures in order to solve a short circuit. Now, tingnan natin yung procedure o yung one by one. You can it is a very, very powerful procedure simply because you can solve a small scale power system to a larger scale system. So it means it can be a smaller system or a larger power system. It is still the same method. Now, you need to have the SLD of the system. Ito yung sinasabi natin na apat na per unit na. And then you need to have a numerical value of the base or your S base is constant. So any number will do. This is the same thing. You will yield with the same result. Third, you need to convert any percentage reactances from its new base. Ang tinatawag dyan, guys, is no other than the period. The modeling of your system to per unit equivalency. And then from there, you can have the reactance diagram as we have discussed from the previous slide. And then you can now get the percentage reactance up to the fault point F or XTH F per unit. This is only the same thing. You can now get the full load current. This is your I base. This is number 5 by having S base all over square root of 3 V base. Okay. And last one on the list, you can now get the short circuit parameters in KBA short circuit or the short circuit three-phase by having the formulas that we have presented and discussed from the previous slides. Now, before we go to the some examples, let us have this envelope diagram. This is an envelope diagram of the fault. Envelope diagram ang tawag dyan. And again, the fault, ganito yung characteristic. At first, mataas siya. And then all of a sudden, it will decrease until it reaches steady state. Kaya nga may tatlong state ka rito. May tinatawag ka na sub-transient, transient state, at steady state. Now, these 3 states are very important on analysis, lalong-lalo na if you're considering post-analysis. considering stability, reliability. It's very important, no? So that you can see what went wrong, no? Anong nangyaring mali, no? On the process, why some of the relays did not trip, nagkaroon ng maltrip. And then, if you want to get the short circuit current, very obvious that you need to have the sub-transient period because dito makikita yung tinatawag nating maximum fault. Di ba? Kasi IF versus T yan. Please take note. This abscissa here, your X, no? Naka-millisecond yan o instead o microsecond, depends on the on the x-axis mo. Kasi in terms of time, di ba? Mabilis yan eh. Kaya nga fault, tandaan po ninyo, fault current. Wala pang nakakakita ng fault curve. You compute it. But again, wala pa nakita isang, tandaan nyo nga eh, di ba? If you blink your eye, 1 millisecond. But if you are struck by lightning, that is 1 microsecond. So, what's the moral lesson of the story? Hindi ka pa nagbi-blink, nakidlatan ka na, deads ka na. Diba? Kasi yan, stroke of lightning yan, fault curve. Kaya wala pang nakakita ng current. Kaya in this case, kaya napapansin ninyo, no, in terms of post-analysis, short circuit, tapos meron kang envelope curve. Ganyan siya. Kahit sa stability analysis. But the moral lesson of the story is, in terms of fault current, we allow the computation of the fault current by using the sub-transient reactants. The other reactants are for post-analysis. Okay? So just use the XD double prime or the sub-transient reactants only. And that is the one who will determine the ISC short circuit. Okay? The others are for the computation of the critical time and the others for the steady state parameters for post-analysis. Okay, now I think much better that we can have an application by having a sample problem. Okay, simple lang ang sample problem natin, no? Simpleng-simple lang. But again, the importance here is you know the concept. If you know the concept and fundamentals, you can already apply it on complex systems. Kaya nga guys, no, if you have a concept, no, kaya mas maganda if you already know the fundamental and concept, because any problems that it will give you, no, you can solve it on your own. Okay, let us have this sample problem. You have a single line diagram of the power system. It is based on the reactance of each alternator as given here. We need to find the short circuit current that will flow into a complete short circuit path at F. So ayan po yung natin. And we have the busbar voltage as 12 kilovolt, no, for this purpose. Okay, now we will make use of the 6-point algorithm. And again, no, it's up to you how to analyze it already because the solution is already given to you. I just explaining one by one, and then from there, just practice that out so that you can fully understand. So in this case, no, using the 6-point algorithm, the SLD is given, right? Now you can choose any number that you want. Now from here, you have a 35,000 kVA. Now this is also the same thing, ha? Parehas ng po yan. kVA, this is the same thing if you use 35 MVA. The only difference is yung numbers of zeros, right? Okay, what you will do on number 3 is you need to have the change of base formula, no, from what we have discussed, no, from the last slide, no. To get X new is whatever the X given is, and then you have your S base all over S given, right? You will make use of this because the system is linear, because the post-fault or the per unit, no, voltage or the pre-fault rather is equal to 1 because there's only one voltage, no, on the system. That's the 12 kilovolt. And then from there, no, from the SLD, using the formula, you can get the new percentage reactances, no? Kaya nga tawag is change of base. You have 70% and 87.5%, right? Following this formula here from the diagram itself, no, from the last slide. Okay, you have J 0.7 and J 0.875 on the reactor A and B respectively. So ito yung sinasabi natin, ano? Oh, nandiyan naman halos lahat eh. And then from there, no, you can get the reactance diagram, no, by having neutralizing, no, all of the sources as I mentioned. So how you will neutralize a source? Kasi magre-reactance diagram ka na and you need to get the reactance up to the fault point, di ba? Thevenin ka na. So since these are independent sources, you need to neutralize the sources here by having Vs is equal to 0, right? By short-circuiting the source. And then represented it by the model, no, na na-compute natin. I think that is J.7 at saka J.875, right? By changing the bases, no, from your, no, changing the calculation using the change of base formula, right? So modeling the percentage reactances. And then from that, no, as we have discussed, we can now get the Thevenin reactance at the fault point from the neutral, no, which is in this case, no, your ground, up to the fault point. And very obvious, nakaparallel yung 0.7 sa 0.875, right? By using product all over the sum. Okay, clear all the paths here? Moving forward. And definitely the Thevenin reactance based on the protocol over the sum is 0.3889 per unit. And then from here, you can solve the I base. So babalikan po natin yan. Lahat ng yan is based on this 6-point algorithm on this slide number 17. And then from there, no, you can now get the IPU and the I base using S base all over square root of 3 of V base. There's only one V base on the system, which is your 12 kV. And thus, multiplying I base by IPU, yung 1,684 multiplied by 2.583 at 5813. The answer is 4,000 or 4.33 kiloamps. Okay. Now, there's an alternative method. Ang tawag dyan is a short circuit component method. Wherein when you say a short circuit component method, superposition theorem ang gagamitin. If you have your generator A and you have a generator B and then the fault occurs here and this is your 12 kilovolt bus bar and you may given kanina dito, what you will do is you need to off one of the, di ba? One of the generators and then compute, no, for the short circuit. Kasi meron siyang ISC at A, meron siyang ISC at B, and you have IF. And definitely IF dependent on the responses. Diba? By superposition theorem. There's a response at ISCA if B is close, right? Or off. There is a response at B if ISC is off. And that's why, you can now get the short circuit current at F by having the responses at A and B. Yung tinatawag nating individual contributions by using superposition. Ang tawag yan is the short circuit component method, which is also very important, no, on design and analysis of your relaying systems. Okay, now let us have, no, this technique. Madali lang naman ito. You want to get the full load current delivered at alternator A, that is S base all over V base. Now we will make use of the 15,000, no, which is given on the problem. 15,000 or 15 MVA. And if you divide it by 12K, the answer is 721.7. Now we need to off, no? We need to off, first we need to off B, alternator B. We will off this one. So kapag naka-off siya, ISA lang ang magmamanifest dito. Okay? Since yung alternator A, pwede makuha natin ng XGA dito, you can now do so. No? How can you get your XGA on this point? So if you have a 15 MVA, I think this is also 15,000 kVA kanina ang given . Tapos this is 30%, no, from the given, because I see here on the solution. If I use 15,000 kVA, kVA as base, no? As base, having B as off. Ang lalabas, di ba, this is the formula, no, for percentage reactance due. Please take note, this a little bit of a common sense method. If S given is equal to S base, the formula for the change of base is definitely S nu is equal to X given na. Diretso na siya. Okay? So whatever the given is, that will be the new value, no, of the base for the reactance. And thus, as you can see, the reactance of A is also 30% in this case. Simply because kung ang given is 30%, ang given is 15,000 at ang base is 15,000, the answer is 30% as well. And that's why, this is the formula kanina, that your short circuit is equal to the I base at A times IPU, or in other words, 100 over percentage XTH at volt point F. Okay, since isa lang ang reactance natin kinonsider, because your generator is off at B. Okay? The answer at the first contribution for ISC at A is 2,405.5. If you do the same pattern at B, considering off, the generator A is off, then it will yield with the same method that we have discussed on alternator A. So, in this case, magbabago lang ang I base mo because the base is already at B. And then the short circuit, contribution at B, and it will yield with the same X given over your X base is equal to X given kasi ang given sa B, if you still recall, going back to your notes, is 50% X at saka 20,000 kVA, right? If you do the same analysis here, the same kVA din ang ginamit, then naka-off ang A, the answer for ISC at B is 1,924.5. And if you add ISC at A by B, it will deal with the same fate or the same result a while ago. That is 4.33 kiloampere. So that's why, guys, if you technically, there are only two methods lang talaga sa EE ang importante. The others are just others. Hindi po ang importante yung yung mesh forever, nodal forever. Ang importante, guys, is the Thevenin's theorem, which is kasama ni Norton's, and the superposition theorem in terms of application. So the student, when you were undergrad, what's the point of that? Hindi lang nararamdaman because the degree of appreciation is dependent on how you learn. If you learn things, you can appreciate things as well, especially this, right? Okay, so I will now go to clear these drawings here because on undergrad, when I discuss this on undergrad, talagang in detail. On your end, an hour or two will do because you're already on graduate, graduates na kaya, So in that case, we'll not go to in detailed discussion. Okay, now let's move forward to another example again. But before we do that, please take note of the following: that feeder loads are considered balanced, but they did not have a contribution to the fault current. Ito lang ang moral lesson dyan. If you see a feeder load, yung mga open-ended load, it does not have any contribution to the fault current simply because the only contribution that will contribute to the fault are those rotating machines, such as motor loads and your generators. So again, the only parameters that will be connected to the reactance diagram are those motor loads or rotating loads. If you see a feeder load, open-ended load, you will not connect it to the reactance diagram, the calculation for the Thevenin's reactance up to the fault point. So we can have that example here. So ito, we can have problem number 2. So the section of a bus bar A and B are limited by a bus bar reactor. So this is almost a ring system, rated 5,000 kVA with 10% reactance. On bus bar A, there are 2 generators having the specifications here, 10 kVA, 10,000 kVA, 10% reactance. On B, you have 2 generators as well, 8,000 kVA with 12% reactance. And then there's a feeder load, which is connected at the bus bar at B with a 5 kilowatt, with a lagging power factor 0.7 placed at section B. If the bus bar voltage is 10 kV, find the fault on this load. If the fault occurs at this load, find the MVA and the short circuit current. Okay, without further ado, if you can see, the problem is a statement form. So you need to draw the single line diagram for this. So it will become like this. By using the 6-point algorithm that we have mentioned a while ago, by having the correct single line diagram based on this paragraph or sentence or in this problem, it will become like this. Okay. Now the fault point occurs at the feeder load. As you can see, the feeder load is an open-ended load. So again, that is not a circle. So if that is a circle, dapat may percentage reactance yan. And at the end, it must be connected at the reactance diagram or neutral. We can use an SBA here, S-base here, 69 MBA. So katuwaan lang po ito. Don't take it personally. Okay, I use 69 MBA in this example so that you can see if you use other MBA bases, the answer will be the same. Okay, now this is the conversion to per unit or percentage reactance yung kanina. X nu is equal to S given multiplied by S base over S given. So again, this is the formula. I will not repeat it again, but as you can see, if you go back to the single line diagram, these are the given values, and the 69 here is the S base, the 10, the 8, and the 5 in MBA is the given on the problem. So ito yung S base, ito yung S given sa ilalim. And if you do the math, ayan na po yung lalabas. The feeder load, you do not need to compute for the percentage reactance simply because they will not be connected to the power system. Okay, you have these values here. Then we will now draw the reactance diagram. As I mentioned a while ago, in drawing the reactance diagram, you need to neutralize all of the sources, and the sources must be short-circuited here. And if that is short-circuited, you need to represent that by the corresponding reactances. These reactances are already computed from the next slide. And if you do so, this is the reactance diagram of this number. Okay. Ayan. And the fault point occurs at that bus bar. And pretty clear how we will do the reactance diagram of the Thevenin's reactance of the fault point F. Nakaparallel ang 0.69, nakaseries sa 1.38, 1.035 is also parallel, and whatever the result of this is XA and this is XB, it must be parallel as well. If you do the math and the analysis, the Thevenin's reactance up to the fault point F will yield with a 0.3981 value. And thus, number 5, you need to solve for the I base as well as IPU. The I base is 3.983 kilo. And the IPU, by having BTH over XTH, the answer is 2.512. Now, the short circuit parameters for the MBA short circuit and ISC at F is MBA times IPU. For MBA short circuit, the answer is 173. And for the ISC at F, I base times IPU, the I base is already defined already as 3.983 kilo. You multiply by 2.5112, which is IPU. The answer is 10K or 10,000 kilo ampere or 10 kilo ampere. Again, what we have already established for the values of MVA and ISC are very important on the how you will determine the specifications of your relays, rather of your fuses and circuit breakers on the next few slides. Okay, I think let's move forward na doon. Ano? But before we do anything else here, you can get the former Thevenin reactance or modeling of a grid by having this relationship. Kasi guys, ganito yan. No? On some single line diagrams, okay, like this, for example, 34.5 kilovolt, tapos nakalagay is you have here 100 MVA o MVA short circuit. This one can be modeled as a reactor. Kasi ito, complex source yan from the top Utility mo ito When I say utility, complex power system mo sa taas yan. And ang sabi ni Thevenin, pwede mo siyang ma-model, in terms of its corresponding voltage at yung Thevenin's reactance. Ito yung tinatawag nating XTH former. Kasi para makuha ang XTH former, di ba? You can still recall MVA short circuit is MVA base multiplied by, considering the complex power system, the Thevenin's voltage or the pre-fault voltage is 1. At ito yung XTHF na sinasabi kong former. Are you synchronizing that? The answer is this, right? You need to divide the MVA base, which is whatever your favorite number is, divided by the MVA short circuit. For example, my MVA base is 24. To get the Thevenin's reactance at the fault point F, 24 over 100. The answer will be 0.24, and that is the modeling. Okay. And that's the modeling for this. Nakalagay J.24. Right? Okay. So, tapos, since this is treatment as a generator, isu-short circuit mo rin siya papunta. This is your V utility 0. You need to short circuit this. Papunta siya neutral. Okay. So, if you encounter a utility grid, so yan ang pagmo-model ng Thevenin's reactance niya o yung reactor niya. It can be represented by a reactor which is called, this my own name, XTH former ang tawag ko dyan. Okay, now we can clear this up and then move forward na tayo. Okay, now the others just if you want to get the specification of your circuit breaker, if you want to get the interrupting capacity, and the momentary rating of your circuit breaker, you can use the formula factor times ISC. Ayan. So yung factor na sinasabi natin dito, yung tinatawag nating cycle duty, Now, dependent on two things. Circuit breaker above 600 volt at saka if the circuit breaker is below 600 volt. Ano yung 600 volt dito? Yan yung tinatawag nating fault point voltage. For example, the fault point occurs at a 13.8 bus bar. You will need to use the following factors. Yung ISC natin, ito yung kinupit natin, ISC 3-phase. Yung cycle duty, ito yung tinatawag nating di ba? Yung or CD, walang pinakaiba yan yung sa frequency. The lower the frequency, the larger the time, or the higher the frequency, inversely proportional frequency sa time. Diba? The higher the frequency, the lower the time, the higher the time, the lower the frequency. Ang ibig sabihin nito, pag cycle duty, kunyari, 3 cycle duty. Ibig sabihin, after 3 cycles, 1, 2, 3, the fault is interrupted. So, ibig sabihin, the lower the cycle duty, the faster the time of operation. Okay, or faster time of interruption. Kaya kung mapapansin nyo rito, no, you can see, no, the following constants in terms of cycle duty. Okay. Now I think on your exercises, I have, no, the following cycle duty there, and then definitely you need to have that factors to be multiplied on your ISC 3-phase to get the following specifications of your relays and fuses. So yun lang naman ang gagawin ninyo, no? Just multiply it by the factor dependent on the fault point voltage. So mas mataas ang MCR kasi this is the specification of the relay with the arcing after the fault occurs. So as you can see here, there are some factors which is dependent on the fault point voltage. Now, again, no, there's a 1.5 here. What's the meaning of this? Ito, anywhere on the power system. But if the fault occurs mismo sa genset, you need to multiply it by 1.5. Hindi po 1.6. Okay? Now, if that is below 600 volt, whatever MCR, just multiply it by ISC. Yung kanina pala, I forgot to mention sa CAIC, if that is low volt, if the fault point voltage is lower than 600 volts, your CAIC is simply equal to whatever your short circuit current is. Okay. Here, all drawings here. We can move forward. And then the others, no, is for the fuses. If you want to use fuse instead of a circuit breaker for the fault point. So equation 4.12, this is the 3-phase interrupting duty or the kVA-ID. If your fuse, if the fault voltage is above 600 volt, you need to have the kVA-ID, which is equal to kVA short circuit. Okay, now you have your CAIC here, no? The factor, you need to multiply it by ISC. Okay. And then, no, the others, no, if this is lower than 600 volt. The factor is 1.6 and 1.25, no, on the system here, no. Okay. Now, in this case, no, it will dependent, no, if the voltage is higher than 600 or lower than 600. So you have some factors that you need to represent on the formula for the fuse settings. Okay, I think that will be enough, no, for this lecture. We already covered all of the slides here. So again, we can now stop the recording.